4 دروع.
واحد، اثنين، ثلاثة،
أربعة. بتكيل هيدا
شو بتكيل يا أخي؟
عند صاحبك اللي حاني بهم بتكيل هيك.
هاي بتكيلك
هيك. 1
شو هالكلام؟
2
شو هذا؟
3
شو 3 شو هذا؟
4
شو
هيك
هالكلام؟
تكيلوا.
لا لا يا أخي،
هيك تكيلوا. لما بيمني
بلا مخربة بلا مخربة شوفي هاودي بلا مخربة ميزان سكين مفتوح اللحمات ما بيسلوا.
And so, as I have said before...
No. The water clock is at last empty.
Enough. Your time is up. The water has all run out. Mud. There's mud in the water clock.
No, you must not. The clock is often clogged with dirt. Why must you clean it now? Why must my speech be made shorter?
Order! Order!
Barter and exchange, forerunner of modern systems of coinage, was a simple, even enviable method of transacting business. But scales that swing in favor of one man must necessarily cheat the other. Primitive means of measuring time, weight, and distance were a part of the primitive life a few hundred years ago. The senses of justice, of fairness, of honesty, of need for accuracy were dulled by man's lack of proper measuring tools. As life's pace through the centuries grew more rapid and its complexities increased, man of necessity grew more cautious, became interested in more accurate means of measuring time, weight, and distance. He began to give more attention to the problem of measurement as it concerned his personal life and the value of his property, and then considered it in relation to his neighbor's welfare. And as horizons expanded and man explored new lands, his methods of measuring distance necessarily became finer. As he became more observant, time assumed more value in his personal and public life, and so his sense of time became sharper. Weights, as diversified as the people who originated them, and most commonly subject to inaccuracy and fraud, also came under man's surveillance. They gradually approached a standard. More delicate, more sensitive instruments were developed to aid him in determining the extent of his possessions and purchases and in plotting his course. During these centuries, measurement of time dwindled from days to hours, to minutes, to seconds. Finally, seconds were divided into hundreds, thousands of parts. Fine measurement did not stop at the weight of a seed, but went on to the weight of a grain of sand, the weight of an eyelash. Haphazard measurement of length gave place to the standard yard, the standard inch, and the single inch was divided into 10,000 parts.
Today, accuracy and precision have taken on new meanings. Split seconds, hundredths of an ounce, thousandths of an inch have become of vital importance in the exploration of new worlds of science, invention, and development. New instruments, new and delicate measuring devices have added to the power of man's senses. Now science knows the answers to such questions as, how long does an explosion last? That question is answered in laboratories where the 24-hour day has been divided into millions of split seconds. How fast is an electric spark? Not so fast that it cannot be measured to the thousandth part of a second by the electric oscillograph. How flexible is steel? The amount of bending of a railroad track under tons of speeding weight is easily visible. But science has gone far beyond ordinary rules of measurement. We can measure the movement of the same steel rail under the light pressure of a finger. With the delicate electric telemeter, the movement in the section of the railroad track can be measured in millionths of an inch, 8 millionths under the pressure of a few ounces. How small is 8 millionths of an inch? Compared with the average thickness of a human hair, magnified thousands and thousands of times under the microscope, 8 millionths of an inch would correspond to the thin white line in the center of the hair. That's how far the finger bends the rail. How heavy is a speck of dust? How much does smoke weigh? How much does a tiny black dot from a lead pencil weigh? The finest scales can tell, scales operating on so fine a balance that they must be enclosed in glass and the air artificially conditioned. Scales so sensitive that the breeze from a moving hand would completely unbalance the indicator. And the answer comes not in ounces, but in millionths of an ounce. A slow, tedious job, weighing minute particles. But the patience of science parallels the precision of its instruments, reaching into the world of the infinitely small, interpreting it in terms of a new language of measurement. The tiny dot from the lead pencil can be magnified until we see the fibers in the sheet of paper, and the scattered bits of black are as big as chunks of coal. With microscope lenses that carry us farther and farther beyond the range of the human eye, we can lose ourselves in a newspaper reproduction of a photograph until nothing is left but meaningless dots. How sharp is a sharp edge? The cutting blade of a pair of scissors, under the searching eye of the microscope, appears rough and jagged. The peaks and valleys on the edge of the blade can be easily seen. What's in a mixture? How many parts of this and how many parts of that? A beaker full of water from a large swimming pool, and mixed with all the water in that pool, a single teaspoonful of salt. How much salt is in the beaker? Finding the answer is as complicated as finding one man in a crowd of hundreds of thousands of people. But the presence of infinitely small particles of matter can be detected when the residue from the beaker is burned and a picture of the flame taken with a spectrograph. The teaspoonful of salt in the swimming pool leaves its signature of tiny lines on a photographic film. Through such precision instruments as these, our standards of accuracy are being changed. Science has opened the gateway to new conquests in accuracy of measurement. The yardstick has expanded until hundredths of an inch. Thousandths of an inch, even millionths, have become measurable quantities. And the power of man's senses has been extended to reach into a new world that he cannot see or hear or feel without the aid of science. A world in which the most familiar objects become strange and unrecognizable, because our standards of comparison have grown infinitely small. Chemists and engineers, the scientists of industry, are becoming more and more familiar with the fantastic land beyond the microscope. Through lenses which magnify hundreds and thousands of times, metal experts count and even measure the crystal structures which make up iron and steel. A measuring stick smaller than a pinhead is used, with tiny lines a thousandth of an inch apart. Under the searching lens of the microscope, small blocks of metal in the laboratory tell the secrets of the millions of tons of iron and steel that go into the huge manufacturing plants And in these plants, microscopic precision controls the form and size and surface of every part. Through the development for factory use of all these precision devices for the measurement of things infinitely small, within limits of tolerance that are almost absolute, we are now able to meet the precision demands of quantity production of fine parts on the basis of standardization and complete interchangeability. Gauges to test the hardness and toughness of metals are miracles of modern precision. A device known as a scleroscope is used to measure the degree of resistance of metal parts such as the camshaft. A small weight in the tube is dropped on the surface being tested. The amount of bounce measures the hardness of the surface. Hard metals are also tested in a large master gauge. The metal is placed on a support and a diamond point is forced into the surface. The distance the point penetrates is measured accurately on a dial to determine the exact degree of hardness. A similar type of master gauge is used for checking the toughness of metals. In this method, a steel ball under great pressure is forced into the surface of the metal. The dent or hollow formed in the test specimen is measured under the microscope. Master instruments check the accuracy of measurements within 0.5 of an inch. Master gauges check the accuracy of tools and parts used in the factories and on the assembly lines. This precision control of manufacturing operations, for example, gives an exact fit between piston and piston pin. The size of the parts is so accurately controlled that if the piston is chilled for a moment on ice, it will contract. And the pin, when warmed, will expand enough so that the two will no longer fit. Under all ordinary conditions, the two parts will fit perfectly. But if we reverse the operation and warm the piston, it will expand again, and the pin, chilled on ice, will contract, and now fits too loosely in the hole. Limits of accuracy in inspection of piston pins are so small that they are almost beyond comparison. Finished pins fit smoothly into the pistons with no difference in size over 1/10 of a thousandth of an inch. Surfaces of moving parts are checked within extremes of measurements that are invisible to the human eye. Sensitive electric meters and delicate feeler points check piston diameters in terms of a single inch divided into 10,000 parts. Cylinders are checked for equal perfection in diameter, roundness, and smoothness. Precision cutting machines shape and round the cylinders. Precision polishing machines polish and grind the walls to smoothness. And precision gauges guide the inspection of the finished work. The pistons move up and down in the cylinders of the automobile engine with just enough room to spare for a film of oil thinner than the walls of a soap bubble. In the careful assembly and fitting together of the parts, many different types of gauges are needed. In the factory, a gauge known as an amplifying indicator is used as a precision check on the fit of the main bearings. A delicate feeler arm which travels over the surface of the bearing is connected so that its slightest movement shows on a dial marked in 10,000ths of an inch. The tools called go and no-go gauges automatically guard the perfection of every part. The utmost precision is carried directly into every step of manufacture. The openings between the two prongs of this gauge have been set according to exact measurements. A valve stem that will not go through the top opening is rejected because it is too large. A valve stem that will go through both openings is also rejected because it is too small. A perfect valve stem will go through the top opening and will not go through the bottom opening, yet the difference is less than the thickness of a hair. Inspection of automobile parts in the factory requires the use of many different sizes and shapes of gauges. Special gauges are used to measure the surfaces of transmission gears. Slight imperfections are magnified so that only perfect gears may find their way into the finished product. The dials detect the smallest variation in the sensitive feeler point as the gears are inspected. Another tool, electrical pickup and amplification, has been perfected and put into use to detect flaws. Does this sound like the rhythmical beat of a jungle drum? Actually, it is the sound of a human heart which science can amplify 1,000,000 times, just as sound can be amplified by measuring instruments in factories to make sure that gears are smooth. Throughout the great manufacturing plants, tools, instruments, gauges work with almost uncanny intelligence, sorting and selecting, checking, passing or rejecting, ever on guard for the slightest imperfection. Accuracy, precision, exactness have been brought to new significance in the microscopic world of scientific measurements, utilizing everything that modern science and research can provide in the way of measurements that are precisely so.